Across Europe, 10 million people are already living with Alzheimer's. It's a disease that gradually robs us of our memory, our identity, and our ability to cope with everyday life. It's a disease we all fear, and we've turned to science to help us understand how to treat and prevent it. And it's the reason I've come here, to London, to meet the 4 scientists who've been awarded the Brain Prize 2018 for their work on Alzheimer's disease. Michel Godart, Bart de Strooper, Christian Haas and John Hardy. This is a story that starts in the 1980s. Who wants to begin this story? Who was in there first?
Well, I'm the oldest. I guess I should start. I think it starts with Glenner and Wong isolating protein from the plaques of Alzheimer's disease and getting the sequence of that protein, and therefore, if you like, giving the tools for the molecular biologist to later clone the gene. Then the story really got going, perhaps, when we found amyloid mutations in a family from Britain, and that started to put the disease in an order. It started to say that amyloid was where the disease, at least in those families, started.
And who comes next in this story?
Well, I think we basically took off with John and what Konrad Bayreuther has done. So Konrad identified the gene by the time and basically suggested that there must be a mechanism which generates this deadly little amyloid peptide out of a huge protein. And but by the time we didn't have any model system to investigate that mechanism, because everybody claimed, well, amyloid is only being produced in an Alzheimer's disease brain and never ever in a healthy person, because we're healthy and not obviously getting the disease. And we turned it upside down and said, why not? This must be a mechanism which is probably conserved during evolution, happens in almost every animal, including humans. And so what I then did is I thought, let's develop a tissue culture system. Let's go into regular human tissue culture cells, something very primitive which you can simply culture in every lab worldwide and check out if they produce amyloid. And sure enough, all of these cells did. My own skin fibroblasts did, kidney cells did, and we could bring in then manipulated genes based on John's mutations and find out how they change amyloid production.
So we have the geneticist coming up with the genes. You've come up with a model, but what's your place in this story?
This amyloid is normally produced, and then the question is how does that happen? It comes from a longer precursor protein, so there must be some scissors cutting this amyloid peptide and releasing it. And so we thought if we can find these enzymes, these cutters, and we can block them, then maybe we have a treatment. So we were very motivated to find them. And so there was a second gene found in '95, and there was the preselin gene, and nobody understood really what it was doing. And so we thought maybe it's one of these cutters, and so it turned out to be true, so we proved that.
Now, this has so far been a story of amyloid. You're Professor Tau. You're the man with the tangles. So tell us the part that you played in this story.
Yeah, so in 1988, we showed by direct chemical means that tau is an integral component of the paired helical filaments of Alzheimer's disease, which are the major components of the tangles. And this followed on from work from other people, like Jean-Pierre Brion in Belgium, who had shown there was tau immunoreactivity in tangles. And this work then led us to identify the different forms of tau that are expressed in a normal adult human brain and show that they were all present in the Alzheimer paired helical filaments. And then in 1998, mutations in the tau gene showed that dysfunction of tau protein was sufficient to cause neurodegeneration and dementia, although they cause frontotemporal dementia, which is different from Alzheimer's disease.
Why is it that when some people die and have their brains examined, they have lots of plaques but no symptoms of dementia?
I think there's a huge difference in the reserve capacity of the brain. Some people have a big reserve capacity, other people don't, and that makes a difference. And of course, having a very high amyloid plaque load, even so you are still healthy, would, to my opinion, mean that it won't take too long anymore to develop the disease, to convert into a disease. So at the end, I think it's just a matter of time.
I fundamentally agree. I think that there's a long period when people have amyloid in their brain and without being sick, but eventually those people will get dementia.